Welcome to Opening Voices. Today, Quentin Adam, CEO of Clever Cloud, is meeting Steeve Morin, CEO and founder of ZML. ZML is a European leading tech company specialized in high-performance AI inference stack. Quentin Adam introduces us to Steeve Morin and his background. They also examine and, above all, explain the type and scale of calculation required by AI.
Hello and welcome to Opening Voices. I'm Quentin Adam, the CEO of Clever Cloud, and I am very happy to welcome you in a new episode where we will meet a new tech European leader, which will be Steeve Morin today. Hello, Steve. How are you?
Hi, guys. Welcome. Thank you for having me, Quentin.
So the goal of this podcast is to explain the European technology and business together and try to understand why European technology are not so lame that some people can say, and explain what we are building on our side. Maybe what we can do for beginning is maybe you can introduce you a little bit. What was your life? Where did you work before? Something like that.
Oh, wow. Okay, yeah. To be honest, it's an exercise I'm very bad at, but I'll give it a try because it's you. So I'm Steve. I'm the founder of a company called ZML or ZML, if you are on the other side of the Atlantic. I am first and foremost an engineer. Worked about 5 years on self-driving cars in the early 2000s. Went to a school named Epitech in the early 2000s as well. I'm starting to get a bit old, I think. Yeah, it's starting to show, you know.
We will not disclose your age. But you're 25. You're very welcome.
I am over 25. Yeah, I'm in the down slope, right? Yeah, but then, you know, and most notably, I worked in a company called Zenly for about 8 years. We were bought by Snap in 2017. Then 2022, Snap killed us, and then in 2024, early 2024, founded ZML. We are in Europe.
You also were a guy who acts a lot of cool stuff. You put the code law into GitHub.
Right, yeah.
You built some HDMI key to view some torrent directly.
You remember
on
that?
TV.
Yeah, that's true. Yeah, that was torrent streaming prior to you may remember Popcorn Time at the time, right?
Yeah.
That we're getting old. But prior to that, yeah, I bundled it into, you know, HDMI keys. That was the early days of HDMI keys, right? Then it got outlawed. Too bad.
Yeah.
But you know what's funny?
Who think it will be outlawed? Who think?
Not me. I don't know, man.
Who can do?
You know, torrenting was, let's just say, useless for a while.
Yeah.
But now it's not anymore, right? Who knew? No, but I always had a soft, place in my heart for a decentralized system, distributed and decentralized system. And torrent to this day is very dear to me. I still donate to libtorrent, by the way.
You know, in Clever Cloud we use peer-to-peer to deploy the system. I think we are the only one to do that, because all of
Alibaba does it.
No.
Dragonfly, that's what it does.
They do it for this part. We use it like.
But there was a famous paper. Oh yes, and about my background, most notably,
is a little bit like. I don't know if you read the
I did, but I've been out for a good while. But you know, in terms of notable achievements, I was the author of Boot to Docker as well, which then became Docker for Mac. Yes, sir.
Yes, Boot to Docker was you also, yeah.
Fun stuff.
Lots of good ideas.
My good friend, Salman. Love you, Salman.
Okay, so and you funded ZML,
right?
What is the reason why ZML is existing?
Because inference is the universal problem, truly universal problem in AI, or at least this was what I was. I would say what I had to explain to folks 2 years ago, a year and a half ago. But inference is the true universal problem, and there's no like you have to be radical about it. And there was nothing on the market, as the next operator of ZML, which was, fairly sizable. We were like the number one spender on Google Cloud for 3 years. So we had quite an operation. And as, next operator of that company, of that infrastructure, right, there was nothing on the market that, was something I would feel confident, deploying. And it felt to me that we were in this, very uneasy situation in which, either you pay money to Sam Altman, which, I would wager he has, plenty of, or, you pay money to Jensen. But I didn't see anything fundamental about this, right? Yes, there's CUDA. Yes, there's thank you. There's CUDA. There's, the networking and all of this stuff. But it's not for lack of, like there's offer of chips. Like there's AMD, there's TPU, there's Trainium,
Okay. What we can do maybe to help anybody understand what we are doing there is explaining how those work I. What we call I, which is a subset of I, which is LLM.
Right.
How does an LLM work from a calculation point of view, and which phase are happening in a calcul, and which kind of calcul are we doing, and why does it not fit in the plain old Intel we all have in our computer?
It actually does in some weird way. So I mean, first things first, right? Maybe as a bit of context before, I explain a bit, how they work at the very broad but, very fundamental level is we haven't been, compute bound in 20 years. We used to be compute bound, but since, about 2005-ish, we were network bound, IO bound, right? Which then made the cloud, made the whole...
Make all the first well-known talks about Clever Cloud explaining to the people that anywhere in the world we have IO problem. Just stop talking to me about calculation in your CPU. You have problem of network and storage.
Rails, right? And Python and so on. So it worked beautifully for like 20 years, right? We were limited by networking, whether it's, and storage as well, but IO in general, indeed. And whether it was, internal networks or like external networks, like 5G and all of these things, right? Well, I would say wireless networks. Mostly an IO problem. And then, what have you? We go back into compute bound problems, right? There's so much thing, like a GPU, let's say, or a CPU for that matter, can do. And so all this infrastructure, like software infrastructure that we use for like 20 years, or at least 15, let's just say, or like, 10 if you, count Docker as the start of, the new generation type of thing. I know you have a sweet spot for that technology.
I think it's I will say it like Go. Docker is a very, very nice technology for a technology from the 80s, but yes.
Remember Solomon is my close friend.
Yeah.
Right? But in all seriousness, like we were essentially IO bound, and we are now going back into compute bound problems. And so a lot of things are, thrown out the window. Knowing this, there's very little, reuse in terms of software infrastructure. We try to, but it's very hard. And so everybody's trying to figure out. And so in the very,
but the reason why we are computation bound in the CPU bound and compute bound in this world is maybe because we change the way we make calculation. What we does with LLM in kind of operation is quite different of what we were used to do, isn't it?
Let's just say that calculations, those types of calculations are not very different in the sense that they were always there. Like, it's just that compute became good enough for it to be viable, right? So it's not a new thing. Like we, reinvested.
But there is a reason why we're using GPU and not CPU is because
mostly because of matrix multiplications. Yeah, but
it's a kind of calculation we don't use a lot in a traditional computing system.
So yes, but maybe like GPUs, what they do is they put us ahead of the curve, essentially. One could argue that those types of calculations, especially in HPC, for instance,
I always been there.
Yeah, well.
But then there is a generalization of the point.
Oh yeah, absolutely. Yeah. But the idea is there's very little reuse. There's new hardware, obviously, and maybe something that's new today is now we have to care about the hardware because we are compute bound, right? So,
but because mostly we're using majority of instruction, we use very little before.
Of the hardware, you mean? Oh yeah. We spent most of our time waiting, so we could abstract it away. This is the thing. You could abstract the hardware because most of the time you were spending waiting for I/O to complete. But now it's not, number one, that's not the case anymore, and number two, you have to care about, essentially you deploy on this precise hardware, right? I recall a time in which, deploying, or let's say, having a 486 DX2 or a DX4 was a very big difference, right? But, if you look at your average, cloud deployment, they use 8-year-old CPUs and nobody cares, right? Because in the end, we are indeed waiting on I/O. And so today, the issue, we're running again into is
it's
we have to care about these things.
Maybe we can explain.
And so,
if I ask something for a network, what will be the kind of different step which will be happening inside the system?
Essentially, the way it works, the way it works is you can imagine you have what's called the latent space, right? And the latent space is, where all the information, lives, right? So for sake of simplicity, let's take a 3D space, right? And in that 3D space, you can model everything, let's say, right? So in LLMs, it's a lot more than three dimensions, but, for sake of simplicity. So maybe, you have animals here, right? And animals, you would have, dogs and cats, and that sort of thing. In this space, essentially lives, knowledge, but also, vocabulary, everything, right? And so what you do, essentially, is you have a vector in that space, right? You have a point in that space, or rather a vector, right? Mm-hmm. And what you do is...
So you vectorize the information first?
Well, let's just say you have what's called a vector representation. So it could be usually we call it an embedding, for instance. But the idea is, for sake of simplicity again, you have a vector, right? Representing, let's say, your query. Or your current token. And you're trying to generate the next token. Token is a bit, of word, right? Yeah. And
it's kind of a syllabus for people to understand, because we can have people which are not technical looking at the video. So basically,
imagine, a token is
first, if you try to request a LLM, first you will cut your sentence into.
So you divide your sentence, let's say, into syllabus, right? So 2-3 letters,
It will be what we so-called tokens.
Tokens, yes.
The thing you don't understand, but you pay.
Pay for a lot, right? Yeah.
The tokens. It's more or less the syllabus.
And the idea is, what you do in those tokens is you try to predict the next one, right? So when you ask a question to an LLM, you divide the text into tokens, and then you essentially register, the transformation between the text you input. That phase is called a prefill, right?
Okay.
And then you ask the LLM, generate the next token, right? So, but you might ask me, but this is not what I'm doing. I'm asking it a question, right? I'm not, generating the next token. Well, you are, because what you don't see is that in the background, there's your question is prefixed by, let's just say, question, the question you just entered. Then the system will append, response, and then let the LLM predict the response, right? So what happens is, and then you generate, those tokens. And so how does it work? At the end of the last token, you can represent it as a vector, right? And to generate the next token, you will apply transformation on that vector. And so these transformations happen in sequence. These sequences are called layers. And so for each layer, you will, take the input, apply the transformations, go to the next layer, reapply transformations, right? And each layer is a series of transformations, but the same always, right? At the end, you get another vector transformed by, the sequence.
The sequence of layers.
Yes, and what you
How
do...
many layers can you expect from at the day a classical LLM like GPT-5?
So GPT-5, it's not public, but if you took like a Llama 8B, for instance, 8B means 8 billion parameters. So there's 8 billion parameters that are, essentially applied to your LLM, to your vector, sorry. It's 32 layers.
32, okay.
But it can go into 80, 100, What's important though is that you run these layers in sequence. So there's a causality aspect to that, right? You have to do one, then do the other. So you cannot parallelize,
You cannot
this.
parallelize the stuff, okay.
All right. Now that we know this, in the end, we get another vector, right? And so what you do in the end, you take your big table of syllabus and you try and find the closest syllabus to that vector. And it's called detokenization.
Okay.
And this is how you get the next token. You apply that token and you restart the cycle over again. Well, you don't start from the vector you just found. You start from the token.
And
Yes.
how do you decide you have enough token? You made a sentence or something like that?
So the model is trained to essentially self-limit itself. So you have a contract with the model it's called a template. And the model may have special tokens to tell you it's done finishing. Okay. But it is up to you to actually do it. You can indeed, what model can signal to you that it's done, and you can tell it, yeah, I don't care, do it, continue. And it will continue until, a lot of times what happens, these models, like they start to loop and they repeat themselves over and over again. All of them this can happen, but in the end, yeah, you have to have a contract between...
Like a long speech of Donald Trump.
A bit more coherent, but yes. But yeah, no, that's the idea. So you have a contract in which the people who train the LLM tell you, all right, this is a special token to tell you that this is the user input, for instance. This is a token to tell you that the model was trained to think that the end of that response is the next probable token, and so that's how it works. And so you have to act on it. Of course, you have to detect it, and then stop generation.
And so
that's how it works, right? It's not very.
What is the kind of operation you do to generate your tokens? What is the kind of
what do you mean?
What is the kind of instruction you give to the computational chip?
Many things. So there's many. Usually they are like bricks, right? What's you have the multi-layer perceptron, the attention layer, the activation functions. There's like many essentially a game of Legos, and you assemble them.
So the layers are not making the same thing all together.
The layers are the same. They do the same thing. So usually it's tokenizing, embedding, layers, detokenizing. And
what
this
do
is how you get the
embedding?
token.
Because
embedding is like
explain this to the guys.
Embedding is like transforming the syllabus into its vector representation.
Okay.
So it's like the table.
So we tokenize. We put it into.
So let's say you
vectorization.
Quentin Adam, right? Let's say we tokenize you into 2 words, right? Then why Quentin? Why not why not letter by letter or that sort of thing? You don't know what a tokenizer is trained, right? So it will try to find, ways to essentially represent most of the text in the less, amount of space. So the idea is, let's say we tokenize you into 2 tokens, right? Quentin Adam, right? Quentin will have a vector representation in that space, right? So there will be so we will have a table of 2 entries. One is Quentin, one is Adam. And maybe another one is Steeve and Morin, let's say, right? What you're embedding is going from Quentin to the vector. So it's a lookup. So embedding literally is like looking up, all right, for Quentin, this is that vector. And in the end, when we generate, we will take, the output vector, find the vector who is the closest. Oh, it's Adam. Off we go. This is Adam. And that Adam becomes the new starting point for the generation. But layers are the same, and layers are a sequence of operations, right? So usually there's like 3 bigs, let's just say. MLP is one, multi-layer perceptron is one, attention is a big one. Attention is for transformers. Transformers are what
is the attention phase? Because maybe we'll...
So attention is trying to figure out, the idea of attention is that not all words are the same, have the same impact, right?
So attention,
so let's say
when you decide what is the important...
Roughly, yeah. The idea is, let's say tonight I'm doing a podcast with Quentin Adam, right? You realize that, Quentin Adam has more, I would say, weight to that sentence that I'm, right, or doing, right? And so attention sort of represents that, right? And so the idea is like the model will try to what's called attend to words that are important to try and generate, the next phase. But the idea is, in the end, you run these layers in sequence, detokenize, and you start all over again.
It's a lot of calculation to do.
Yes.
That's way a lot of calculation. That's just like, for example, understand SQL request, put it in an engine, store it in a. It's.
But it's not.
What is maybe it's a stupid question, but what is the kind of ratio of number of calculation if we go on pure number of CPU requests? But
I know.
Can we say just like it's not the same amount? It's not the.
No, it's like
it's not the same world. In fact,
millions more.
It's billions more. Billions more.
But
so it's way a lot of calculation.
Yes, but you have to understand one thing that is very important to understand about essentially neural networks and say AI in the way we talk about it today is that these behaviors are like emerge from it. So what you do is you assemble Legos and you hit it enough that behavior emerges. So it's not like something you bake in. So it's hard to say whether we should do 100 million more calculations than 10 million, right?
It's just I'm trying to make people realize why it's so a big change, and why it will be a change from a financial point of view. So I'm trying to figure out to the people that why AI is not traditional IT. And what's different? It's not just a simple software we put.
Right. So
and that's why I'm asking this kind of question, saying like, okay, can we make the difference? Because like sometimes we say to the people, we switch to C to Java, and it's different because we switch from a static language to interpreted one. And yes, there is a few more calculation, but we win a little bit because of just in time and stuff. And so we roughly will cost us like 30% more requests to the CPU, right. And that's it. But there we are not talking on the same amount of needs,
Right. This is true, but so there's a few things. One is, number one, my bet, or at least my goal with ZML is that we get to reuse, a lot of that infrastructure. But
we will explain that.
No, I know. But the main, fundamental problem is that these tools were built on assumptions that don't really hold for AI. One is that indeed we are compute bound. Yes. The second assumption, so that is a new thing, right? And it's different from, overloading your production. It's very different, right? Because at some point the chip, the numbers a chip can do are not very large, right? We're talking like, tens of people at the same time, not 100, right? So imagine you have to do web with a server that runs at like 16 people requests per second, that's not a lot, right? Or can serve, at most, 16 people at the same time, right? You can imagine, like, this is a ballpark.
Like launching free mobile.
I love them. I love you, Xavier. But the thing is, this is one thing. So compute bound. Second, of course, the amount of money that you have to spend for what you get. But the kicker is, so this, by the way, all this infrastructure, this software infrastructure was built on those assumptions, right? So there's adjustment to be made. The last one, and probably the nail in the coffin, is that LLMs, or at least AI in general, is stateful. The state of a model has to be kept somewhere, and that state is fucking big, right? We're talking for like average conversation. Well, actually, I can give you a number. Like we're talking like, 200 kilobytes per token of state that you have to keep.
Per token. And an average conversation will be
a few thousand tokens.
A few thousand
if you count the system prompt, etc. So there's ways to mitigate that, page attention and so on, but that doesn't change the matter. The matter is that state is big. That state, but that state is big. State is called the KV cache, right? And the KV cache is the rock in your shoe. It's big. It's kept in the most premium asset of modern computing, which is GPU memory. And did I say it was big? Because it's fucking big. And so you cannot freely move it around.
And
right?
At the beginning, the GPU was not so rich in memory, because
yes.
in the traditional GPU usage, we don't need a lot of memory. We need a little bit of memory, a little bit.
Of course, because you do what's called dense calculation.
Yeah. And we have like very few storage to do and stuff. So what we learned this week, because the podcast is divided in weeks, so it will be like several episodes. So what we learned this week is basically one of the big points of AI. It's a leapfrog in the number of calculation we need, and it's kind of calculation we didn't used to, and that's part of the problem ZML is trying to resolve.
Yeah, but here's the thing: there's one piece that that gets overlooked, not by the people who run these systems in production, because they realize it's a very sour surprise, and that surprise is because the state is so big, you cannot freely move it around.
Yeah,
which means you have to keep it where it is. Which means your system is now, have to be stateful, and it has to be fragmented. So you run into fragmentation issues, you run into subscription issues.
You have to have sticky session.
Absolutely.
Which is an anti-pattern for the last 20 years.
Because if you rebalance,
you need to move the fucking context.
Yes, and so
the KV cache will not.
By the way, for the people who had to operate Kafka in production, they know what I'm talking about, like what a rebalance can be painful. But it's the problem with AI.
It's worth for absolutely every distributed system.
The problem in AI though is that essentially you are between a rock and a hard place. There's two solutions to that. One is you transfer the data, but you very much get the risk of overloading the network, essentially, shooting yourself in the foot. Or you say, you know what, screw the state, I'm going to recompute it. Good luck, because you are already compute bound.
Yeah.
So there's no free lunch.
Basically, what we say is using neural network and LLM is using the kind of calculation we're not used to use this intensively before. And we use a lot of intensive computation, and more, the kind of data we use are more heavy. That means that we need to stay them on purpose. What I have heard about AI, and maybe you can correct me on that, is there is difference between when we train the model, we assemble the model and we create it, which is the training, and when we use a model, and which calls the inference. So basically, when OpenAI is creating GPT-5, they are training. When you are using GPT-5, you are using the inference. Can you explain like a little bit the difference between the two procedures inside the system, and what's the difference?
Yeah, like roughly speaking, training is essentially an assembly of two phases or two passes. We call it, one we call the forward pass, the other one we call the backward pass. Right? At least not all AI, but bear with me. Training is saying, hey, you are Steve. And or rather, who are you? And you will tell me, I am Steve, and I will tell you, no, you are not. You are Quentin, right? And maybe, after like 10 times I'll tell you you're Quentin, you will say, okay, Quentin is the guy with the suit, and you will try and find, why, what's the difference between what you think is the response and what the response should be, right? Which is, why we say that, or at least I say that, in AI, behavior emerges, right? Because in the end, you try and find, why it's Quentin, the response to the question. And so forward pass is asking you the question, and you're responding. And backward pass is me telling you, let's measure the difference between, let's say, Steve and Quentin, and apply it to the forward pass in reverse, right? And so this is training. So training, we train a model to do a certain thing. That's why, it's a beautiful word, training, right? Inference is when we ask the model to infer a response. So we run only the forward pass. We don't correct it. We don't tell it, what it should be. We just let it, because we think that it has seen enough to infer a response.
Like you have seen a lot of a cup in your life. When I give you a cup, it's a cup. You don't need to train to being a cup. Right?
I am GPT-5 level in cups.
Yeah.
Yes.
So in terms of economics of calculations, what is the real difference between a training and inference? Because like when we talk about AI, a lot of people are saying like, this is a nightmare. Data center for AI is so big and stuff. And maybe there we need to explain a little bit the difference between the two phases.
So it's, they obey, like, even without economics, they obey for very, very fundamental tectonic forces. In training, you are trying to build one of something, which is, the model, right? So you're trying to, train a model enough so that in the end you get one thing, right? And so in that phase, it's more like, it's a lot comparable to like research, right? You're chasing one goal, one instance of that goal, rather. And in that realm, more is better. You want more data, you want more compute, you want more, more of everything. More is better. So this is training. Because again, you're building one of something, right? On inference, though, this is the complete opposite. You are running the model like billions of times, and you're trying to optimize it. Not so that, it becomes, feasible to train it in the first place, but to operate it in a cheaper manner, to grow your margins. And so, very, very different. It's production code, right? So it's not about doing it once, it's about doing it millions of times, right? By the way, in trainings, details don't care. Because training is research. In productions, details are what gets you. Like if something breaks, somebody gets waken up, right?
Yeah.
And they have to fix it. And so in that realm, less is better. You are better off with less compute. If you can do the same thing with less resources, you will absolutely do it with less resources.
So basically what we can say is training can be a kind of a place where we can try new stuff, not be optimized and everything, because it's a one-time
let's just say
stuff.
You try and optimize certain things that in inference are really, not the thing that you may care about.
And so basically when we built the model, you just duplicate it and you can use it for inference.
Yeah.
And so there is few people in a few places in the world that will create model, and so training capacities will be like kind of anomaly, and inference will be it will be like 99% of the calculation power we need.
Inference?
Yes.
Yes. No, well, maybe I'm trying to be conservative, like 95, but yes.
But anyway,
At least an order of magnitude, yeah. More than training.
I have been told that NVIDIA card is something you cannot not used for the training because they have some particularity in kind of calculation and network between the cards that nobody else have. So for the training phase, they are pretty much the most important stuff there.
It's not really. Maybe circumstantial. Like, so if you're talking about InfiniBand or that sort of thing, this is not really true. This is circumstantially true. Let's just say.
Explaining you.
Circumstantially meaning that in the end, the networking, you move that around. So it's just, how big are the pipes? And so, yes, there's a question between, let's say, InfiniBand 900 gigabit and Rocky 400, like 800 gigabit, right? But does it matter? Not so much. What does matter, though, is that, the CUDA ecosystem, which is CUDA is how you program NVIDIA GPUs.
So CUDA is a library built by NVIDIA, like no.
It's the ecosystem to this. Yeah. It's more like of an ecosystem.
Just maybe the people realize that I think I heard about CUDA for the first time before 2010.
2006.
Yes, it's 2006. I would say it's a 20 years
or roughly.
old. 20 years old.
Yeah. It's been around for a good while. Okay. But it's not a new. At the time, that wasn't a new thing. What was very cool about it was called GPU at the time, General Programming GPU. And at the time, what date?
2007.
Close. Not quite, but close.
The first version. That means you have access to something at 2006.
Oh yeah, I had folks who were doing GPU at the time in 2003 or 4. Right?
Yeah, sure.
But the idea is, it's so CUDA is heavily integrated. So if you play into the CUDA ecosystem, yes, life is good. And on that sense, NVIDIA is far ahead of the curve. But I would say, it's very circumstantial, in the sense that, number one, you can absolutely build something out of integrations, right? You don't have to, buy a ready-made thing, right? The question is, like, when you train, how do you do it? And, what do you prioritize? Do I want to really build, a framework or like software infrastructure for training where I can just, use NVIDIA's? But also, on that matter, probably the most mature ecosystem is the one from Google for TPUs. TPUs are far ahead of CUDA.
Maybe we can discuss about the TPUs a little bit later, explaining to the people kind of sure.
But essentially they're like Google GPUs, so to speak, made by Google. But the idea is, so the point is that it's not really true in the sense that
CUDA is built by NVIDIA and fully integrated by NVIDIA, and that's why they have this
by NVIDIA for NVIDIA.
Yes. So once again, software is leading the way. In this.
This is why I say it's circumstantial.
In this huge hardware discussion, because right now, when people are speaking with investments in Europe, basically you see all the people from telcos and hardware and like nearly public works and stuff going on and say, yeah, it's our job. And what I'm trying to explain to the people, like each time we talk about digital stuff, it's a software problem.
No, I mean,
you need to listen to people.
Let's just say, like, there is hardware, absolutely, but in the case of NVIDIA, it's not the only hardware, and for that matter, it is not the best hardware. There is more powerful hardware available, right?
But it's the best ecosystem from a software point of view.
Exactly. Or let's just say an integration coherency point of view.
And this software is not a project coming from ChatGPT minus 6 months. It's a 20 years old work on how do we do to this kind of calculation, even before we think it can be used in this kind of situation. Like
But to be clear, that was not something like they invented. This is something they invested on. It was existing before CUDA. Look it up. It was called GPGPU, and prior to it being called GPGPU, it was just like doing A plus B in a pixel shader, right?
Okay.
So programmability of GPUs, in what used to be called shaders, is a very old thing. It was used mostly for style, lighting, etc. But it was used to essentially apply functions to pixels. That's why GPUs are massively parallel.
I'm smiling because for the people that don't know, that the first company I created was a company of video games, and basically I play a lot with shader.
There you go.
And it's like I remember to the good old time of making play with shader, because shader is a kind of programming which is really fun, because it's very beautiful. Like at the end, you can make like the 101 of shader is creating fireworks display. Like it's basically the tutorial of how to make shaders and it's very beautiful. Actually, it's a mathematical art.
But you know what? It's not a surprise that GPUs were used, very early. I would say in the modern, 2010-ish AI, because a lot of AI was built on recognizing images, and so running what's called convolution. So essentially applying a model to like pieces of an image. Again, which plays into the massively parallel, nature of, let's say, ingesting pixels.
So basically, there are the time where you train and the time with inference. And if we're speaking about the AI adoption, that what we just discussed plus a derivative was how much the importance now is on inference. And what can we say about inference and the goals? Because we're speaking about building new kind of data centers, and maybe we can have a little bit zoom inside what is a data center and why we speak about power load.
Yeah, we
in
switched
the data
to power.
center. Because so for years, data center have been basically rented to the users by square meter.
Right.
And now we have a lot of densification of the hardware. Basically, you can have nearly the square meter you want in the data center, because the point is power. And the data center have never enough power for all the space.
It has now become the limiting factor, which means this is now what is priced.
I'm still no, it's why it's priced now.
Well, let's just say in the narrative we hear, right?
I'm still trying to convince the data center I am in, like the free spot can be very well used to make saucisson dry, but they don't want it. But the point is, so what is the kind of factor we can describe there, so the people can understand the point there?
So, number one, it is impossible to, or at least very inefficient to think of this whole thing in as a stack of layers, in the sense that everything is intertwined. So, what do I mean by this? Today, infrastructure training, spearheads AI. It's about who has the best model. It's about who can let's say go to AGI, like artificial general intelligence, or like artificial super intelligence. But so let's just say it's a search for the singularity, right? Singularity being like the model is so good that it improves itself, type of thing. So training, essentially is pulling everybody with their own essentially needs, right? And one of these needs is, again, more is better. More is better. So more power. So at one point it was the square meters that were the limiting factor. Because in the end, if you run out of space, somebody has to build the space, right? And at some point, we had too much space, but not enough power, because these chips are terribly hungry of power. So you add more, now power becomes the limiting factor, which then makes power the premium of all of this, because somebody has to dig the trench and get you the wire, and arguably
and someone have to produce the power at some point.
So yes, and so right now, arguably, it's a lot harder to dig a trench and put a wire into the ground than it is to build a new a bigger warehouse, right? It used to be that building a warehouse was out of the question.
Now between the wire and the server, there is a lot of industrial stuff in the warehouse, which are very complicated, and we change a lot of the price of the square meter. Because basically, you need to understand that a data center is priced by power by square meter. So because if you have some power in the square meter, you will have to cool it because it will be warm. So if you add some power, you need to stabilize it. So it's a lot of industrial electricity stuff that are basically make sure that the electricity you use, the tension and everything is very smooth, because when you put a few hundreds millions of hardware in chips, you don't want that the electricity can kind of a spike and burn it.
Yeah, but there's a thing too. There are things that you described that are incremental, meaning, all right, we need, let's say, more coolers, more power stabilizers, right? But this is incremental, right? You do what you used to do, only you do it, with slightly more scale, or maybe even bigger scale. But, that exists into a realm. At some point, you hit the limit. One instance, for instance, I was, told about was that, so, data centers have to have, power generators in case of power failure, right? So they have diesel generators. But at some, scale of wattage, right? The amount of fuel you need to have on site, makes the data center as, let's say, a sensitive,
Yeah, because it's a lot of fuel.
It's a lot of fuel at the same, at the same spot.
To run it.
And so at some point, so it may be a legal limit, it may be a physical limit, but at some point you reach the limit, and then it's not like do it a slightly bit more expensive. It becomes, you have to recurse into a whole new realm, right?
And more
many such cases.
And another point is all this industrial stuff we build in the data center to be able to manage 100 kVA, for example, per rack. If we use only 50 kVA, the industrial stuff we are producing and make to be able to consume 100 kVA is still there. So it makes the kVA way more expensive.
And by the way, that is, all of these discussions assumes that we have power available. At some point, you hit another limit, which is somebody needs to produce that power, right? We need to transfer it, but we also need to produce it. And then when we hit there's not enough power produced, period, the only recourse is we'll need to build a nuclear reactor or something, right? Yeah.
That's right.
And so at some point, that's another, set of problems altogether. But so this is, by the way, training. Training is incentivized to consume more, right? But inference is incentivized to consume less by design.
How can we make inference viable? Because basically what we can see is today AI is a candidate for enter in nearly every process, every knowledge, every need of the industry, of the service, of many things. But it's still like you say, it's expensive because each time you rack a computer in AI, it's a very expensive computer. The server is costly, and the computer will not be able to serve thousands of customers at the same time, but just a very few. So
Right.
it's become very costly. And how can we make the AI industrial? Can we cut the cost? So what's it about?
Right.
And what's happening in this world?
The maybe as an intro, essentially, or without talking about too much, what we do at ZML is AI is essentially on two parallel paths. One is AI as the product. So think of it like OpenAI, like ChatGPT. And the other is AI as the primitive. So AI as the primitive is how AI penetrates the entire economy. Because you build verticalized products for, I don't know, doctors, for like HR, for whatever, on top of AI. And these things are number one, very different. But right now, what we're chasing is AI as the product, chatbots, if you will, or virtual assistants, right? In order for essentially inference to take off, inference will take off in the form of a primitive that every company uses one way or another. But they will not use it as a chatbot, they will use it as a primitive on wheels they build on top. So the evolution, and this is why, by the way, we call inference the universal problem. A bank will do inference. A startup will do inference, either directly or indirectly. But they will build on top of it. They will build products, there will be processes, there will be whatever, right? But everybody will do it. And this is, how we think what we call the AI-powered economy will, exist, rise. And this is what we're chasing, by the way, at ZML. And so, today, the economical unit of inference is what's called the token, which we covered in a previous episode, I might add.
Yeah.
So, the first? What was the first? All right.
Yeah,
so tune in on the first episode. 2 weeks, time flies. Right?
Time flies.
It feels like half an hour, right?
Yeah.
Incredible. So tokens are economical unit of inference for many, many reasons. But it is very essentially LLM chatbot centric. For AI to become a primitive, we have to extract ourselves. And so what we're chasing, or what we'll see, is that once we essentially make the efficiency gains, let's just say we prevail on the less is better journey, then this is where, the amount of compute dedicated to inference will explode. And so right now, the limiting function is not so much the amount of compute available, it's also the price, the operating complexity, the privacy aspects. There's many, many aspects. But at the very bottom of that,
the delivery of the hardware also, because it's
for training, yes, not for inference.
Yeah, for inference, it's okay.
For inference, it's absolutely okay. There's compute available.
Not only NVIDIA, it's okay for inference.
Even for NVIDIA, there's many. I would say there's many things we could argue about this, but for sake of argument, let's just say that even with NVIDIA. So, by the way, when we're saying, OpenAI pushed their numbers out of how many tokens they generate per second or per minute. Anyways, when you do rough calculations, you get into, let's say, the tens of thousands of GPUs, not the 100,000s of GPUs. I don't have the number, by the way. So I did, back of the envelope, right? But you get maybe, and probably less than 50,000. So not like, a million GPUs. For training, that's very different. But for inference, at least on the numbers we've seen, we can make, I would say, some guesstimates. Maybe, let's say maybe 500,000, right? But that's not like, 5 million. That's not 10 million. That's not, So, by the way, that number is bound to grow a lot.
Yeah, because right now we're just at the beginning of the usage of
today,
AI.
the amount of data of compute available for inference it's there. Then if you account,
we want to understand that. We all think it's just the beginning of usage, and just have a look at how much it have changed our life already, and how it's changing the society. And we are at the very, very bottom. So basically what we will see is a fucking total revolution. It's something like very, very...
not very often that we see something like that. Yeah, definitely. At least in my 23 years of career, there were not that many, I would say there were not that many, as big as revolution, or at least something that would totally penetrate the economy, right? There was self-driving in 2017-ish. Then there was the cloud, the mobile revolution. So probably it will be like, mobile, yeah.
And maybe even bigger.
Probably even bigger, but mobile at least in the...
From a financial point of view and how the economics work, I think it will be like...
Let's just say penetration will be faster.
Yeah, sure.
Because the networks are here. Even if it's mobile scale, it will be a lot faster because infrastructure is there, at least in terms of distribution. In terms of compute, questions, right? But then if you take into account like non-NVIDIA compute, there is compute available for inference. Right now it's allocated to training a lot, right? So there's this rush, but there's things on the horizon about inference.
What is under the horizon about inference?
New chips, of course,
So who is producing chips? It's only Intel, AMD?
So number one thing that's very important to understand is GPUs, number one, are a good response to, the AI workloads, calculations, but they're not the only response. And also they're not the most efficient response. And so they're not the only response. GPUs are not the most efficient response. There are chips because, usage is growing, demand, there's demand. There are chips that will come to the market that are able to do that, a lot better or a lot faster or a lot cheaper, right? In the end, though, we are bound by the laws of physics. We will not change. But, there are some efficiencies and sometimes a lot of efficiency, like we're talking hundreds of times, right?
Yeah.
Of gains we can do.
We are not talking about like 20% gain.
No.
Like we're talking about like 400, 800 times.
Probably. And by the way, it's not only hardware, it's also software as well. There's a lot of, overspend, a lot of waste. Not waste, but at least there's a lot of things we can, make a lot more efficient.
What I sometimes when I talk to people and they say to me like, how do you say that it can be like optimization on the AI because the people that are doing it are very good, and I try to explain that yes, but it's a gold rush. So like,
of course,
basically everyone is running on the front, and they have plenty of money to doing it, and they are in the competition, and they are absolutely not doing the optimization because they don't care. This is not the problem.
Capital is bankrolling it for now.
Yeah. And
by the way, on training again, if you are doing inference, at some point, somebody will knock and tell you, "Hey, what the fuck," right?
And right now there is plenty of place in the software. Maybe you can explain me what you explained me like a few months ago. The AMD. Two libraries from AMD where there was a bug. Just to giving an example of this kind of
there was a bug in the AMD compiler, in which it would generate code for, I would say, the wrong GPU versus the one you had, and that would essentially create a 5 to 10x performance regression.
And how many characters do you change in the code to fix it and gain a 10 times 10 characters?
Yeah. To just by the way, mind you, to be important, that was in March this year, right? Not 3 years ago, March this year. By the way, we're talking AMD, right? But there were some things on NVIDIA software too. Again, this year.
But just because people don't have enough time to just like discuss together and make the optimization they can do. So right now there is a lot of optimization place because everybody is rushing, and right now we are speaking about industrialization of AI, and if we want to industrialize, we will have to push the optimization.
For inference, yes.
For inference. When we say we have the inference optimization, like you say, you can have other kind of GPU. So there is something in Google which is old and interesting, which is the TPU. We speak a little bit last week. So can you explain the TPU, and maybe we can open to other chips provider?
Roughly speaking, TPUs. So for number one, GPUs stands for graphic processing unit. CPU stands for central processing unit. TPU stands for tensor processing unit. A tensor is, let's just say, the unit of data in AI. So think of it like a matrix is a tensor with 2 dimensions. A vector, a list of numbers, let's say, is a tensor with 1 dimension, and so on and so on, right? So TPUs are dedicated, made for chips to process tensor data, matrix multiplication operations, etc. They've been around since a good while, like more than 10 years. They are now in generation 7. They're about to ship generation 7. And so Google has been, doing it for a long time.
So it's their own chip.
It's their own chip.
And they're working with their own driver, and they're working in their own software stack on top of that. So
and by the way, it's very different from a GPU. Very, very different, fundamentally. And yet, it works, right?
Yeah. And when Apple is speaking about NPU,
it's the same thing. So of course, everybody's rushing to grab because TPU is probably a trademark or something. So then NPU stands for neural processing unit. It's the same thing.
And how?
Well, not the same thing at the silicon level, but it's the same purpose.
Is the NPU inside the M processor of Apple similar in this work than the TPU of Google, or it's like totally different?
Very different.
And if we open to the other,
but it is made for the same purpose.
It's made for the same purpose, but with a completely different approach.
Depend on how you look. It's. I'm sorry.
From the moon.
It's a tiny bit complicated. Let's just say that it's made to run AI workloads.
Okay.
Both of them.
And those.
There are different approaches.
Can you explain what is the kind of different actor you have there creating new kind of chips? Is there only like the big one, Google, NVIDIA, Intel? And can you describe a little bit this area?
Yes. Number one, GPUs are a good hack to do AI. It works well.
And it makes NVIDIA rich.
Oh, yeah. Of course, beyond measure. But it's not the only thing. Well, it's because it's massively parallel.
Yeah.
But there are some, let's just say, some less than, I would say, shiny things, right? So there's a lot of things one can do to make this more efficient, or faster, or cheaper, right? So there's been, like, for a while now, a rush to, bring new chips to the market that are not NVIDIA, that are essentially purpose-made for this. What's different about that revolution today is that essentially LLMs are different. It was done for a good while to essentially do either signal processing or image processing. But LLMs, they're big, they're heavy, they're like unwieldy. That changed the whole landscape. But in the end, there's still a lot of, I would say, efficiency to get from that. And so these folks started working on it. And so there's a lot of manufacturers that are working on we call them like GPU-like in the sense that you could compare, to what you do with GPU. You would have tenstorrent, even if fundamentally tenstorrent chips are very different from GPUs, but you would use them in the same, you could use them in the same fashion. Tenstorrent, yes, Qualcomm is announcing one.
Qualcomm?
Yeah. It's not very hard to make an AI dedicated chip, fundamentally.
Is it?
There's many tricks, but it's not like a CPU, for instance.
So it's more simple to do AI-oriented chips than a CPU, for example.
Yes, absolutely. For like lots of reasons.
The Intel guys will have a lot of pleasure to
the Intel guys,
because the stock market is failing better.
The Intel guys have more to worry about. But I'm rooting for them. I mean, look, I was a kid in the 90s, so I am still, deeply...
To be fair, I think that the problem they have is they don't listen to René when they say we go full ARM, and I think
Intel?
Yeah.
Why would they?
Yeah, sure. But she was still the vice president. So
x86. But anyways, yeah. For instance, tenstorrent, you would say, we have our homegrown, a company in France called Visora, which actually just taped out, like I think 2 weeks ago.
Maybe.
No, depending on the release.
If you want to understand what is a tape out, there is a series of interviews with Cyprel on this very own channel. And it will explain you a little bit the different culture and works and workload of the semiconductor work. So you will understand what means tape out.
Yes, but let's just say it's becoming a real thing.
So Visora is a company like how many money you need to do that? But how many people is in Visora?
I don't know, but I would say a few hundred, maybe 100. I don't know.
Few dozens.
Few dozens.
Yeah.
Go Visora then. Yeah, good, very good.
Something important that you need to figure out is, for me, right now is reopening the market of the semiconductor and chips to new kind of interest, new kind of companies, because there is an open air in the market. There is a blue ocean. So there is innovation in the semiconductor market that we never seen in the last 25 or 30 years.
This is general with respect to AI. This is the thing, what's very cool about AI. It very much is blue ocean in the sense that geography doesn't really matter anymore. You can, because everybody's trying to figuring it out.
Did you talk to the people of Furiosa?
In South Korea, yeah, Spin Cloud, Germany. I think Germany, right? Yeah.
Yeah, it's Germany. It's a partner of the cloud. And you.
I know. Well, yes, but these days I'm trying to be very careful about, because there was this company, I don't remember, like I think they were from Germany and they were not, and I was like, man, the guy was from Germany, but not the company.
Yeah.
So anyways, yeah. Geography doesn't matter as much, and there hasn't been an opportunity like that in a good while, in a very long while actually. So yeah.
So right now, what's happening is we're creating new kind of chips. Does NVIDIA is also creating chips dedicated to that will be more efficient than what they do?
It's complicated because they can absolutely, by the way. They would have no problem doing it. The issue, though, is that how do you do it without cannibalizing yourself?
Yeah, so they're basically trying to figure out when it will be the good time to launch.
They have this new thing, Robin CPX, that, for instance, does, AI dedicated. So what they do is let's say, AI flavored GPUs, right? As opposed to,
anyway, they still continue to maintain the CUDA.
We'll see
overloading of course, the ecosystem.
What we see is it will be interesting to watch. What we can be sure of is that they absolutely have the firepower to should they feel threatened to come out with something.
Now that we have make a little bit of comprehension of how works the market, maybe we can explain what does ZML and why are you speaking about all of that? Because from the now on, we don't understand what does ZML on this stuff.
What we are doing is everything from where AI is today to where we think AI should go, which is becoming the foundation of the future economy. On that journey, what we do is products, technology, algorithms, architectures to serve that purpose. One of which is completely commoditizing the compute that runs AI. Meaning that freely change between chips, compute chips, in the sense, number one, for what's available today, but chips, past, present, and of course, future. So at the very bottom, of our, I would say, technology, we have software that can run on any compute, any chip, any hardware, for any model at maximum compute capacity, without compromise. Because of course, if there's a compromise, then it's very different. It's a very different choice. And in the end, everything we do is bridging the gap between the AI that will essentially infiltrate the entire economy and where AI is today, in which it needs a lot of efficiency gain, a lot of user experiences gains, a lot of architectural changes, a lot of compute changes, a lot of commoditization for that to happen. The problem, though, is now we need to fast track this. And we cannot wait, 10 years for this to happen, because it will happen eventually. But right now, we are racing to do this.
So basically, what is the kind of blocks you need to build to do this kind of stuff?
Number one, at the very bottom, you want to be able to number one, you want to be faster. You want to use existing hardware better.
But existing hardware can be NVIDIA or non-NVIDIA?
Yeah, it doesn't matter. But you want to be faster. You want to be more efficient. You want to be cheaper without changing anything. Software is easy to distribute. Hardware, a lot harder. That's number one.
And hardware is invested and amortized over the time. And it already have a business plan. So.
It's atoms that have to be moved from moved to be, not made, but at least transformed, moved to be one place to another. And it's there already. And we have to use it to the full extent. There's a lot of room for improvement on existing hardware. Whether it's engineering related, architectural related, mathematical related, all of the, all of this combined, this is number one. Number two, you need to bring optionality. You want, because it's one thing to be faster on the same hardware. It's another thing to have access to better, cheaper, more efficient, more local hardware. So this is the number two thing we bring on the table, which is optionality of compute. You were on say NVIDIA. Now you can add AMD to the equation, let's say, or TPU or Amazon Trainium. And this is about essentially chasing efficiency. So today you have optionality of compute. But what's more important about optionality of compute is that you open also the door to future chips. So you are not bound by essentially everything, or anything NVIDIA does. You can freely navigate into whichever best chip is, serves, you best. That's number two. Number three is operating complexity. So how hard is it to do it yourself? How hard is it to operate these systems? Whether you buy them or you run them or whatever, or you rent them or you whatever, there's an operating complexity you need to solve. And so, and in the end, and finally, of course, all of this gets into the financials, the privacy, the security, the efficiency, anything, the business model, the pricing model, the economic units, everything is addressed by these three things. Because if operating complexity is very hard, you are maybe tempted to go back to tokens. But then you give away privacy. Bringing down operating complexity, being faster, being more
optional,
bring optionality of compute, or at least to say commodity of compute.
Yes. Possibility to just like change and reopen the market of what we provide you the stuff.
Let's use one of the oldest tools in capitalism, which is competition, to our advantage. This is the idea. But also, it's about opening the door to breakthroughs, evolution, and hedging all our bets. Maybe there's like this new company that does, very breakthrough things. There's many of them. But the way to operate their chip is very different from NVIDIA. How can I get those benefits without paying the price, or at least the operating complexity? Because by the way, operating complexity, there's operating complexity related to the hardware. There's operating complexity related to AI. They are different.
Yeah,
but in the end, it's about complexity.
Statefulness is bringing
one of
lots
which, yes,
of complexity.
Data movements, all of these things. So, but I think these are the three things, and the journey of ZML is addressing those three things at the same time by the same people with the same products and the same technology.
Where are you today?
So
on the journey?
Pretty good, pretty far, because we now have technology that runs transparently on at least 4 platforms, many incoming, but...
Which are the 4 platforms you...
NVIDIA, of course. AMD, the contender. Google TPU, the dedicated, AI chips, and Amazon Trainium. So the idea was we get the leader, we get the competitor, and then we get the readily available AI dedicated chips. TPU, Trainium, you can get them right now. You go on your Google console, you say, all right, TPU, boom, right? They are already available, distributed. Chances are you are already an Amazon, let's say, customer, right?
Yeah.
So they are freely available. Freely as in...
They are available in the market if you are in the cloud of Google or Amazon.
So these are the 4 platforms
and you're working.
By the way, if you run on Amazon and you're buying NVIDIA on Amazon, why would you?
Because today you have a software problem.
Let's keep the middlemen. Yeah, but so without ZML, you might think, but the Trainium stack is hard, right?
Yeah.
So that's a huge investment for me. I need to spend a lot of time and energy and money, and you get into this very complex problem, in which unless you are like a very big company, doing, let's say, Trainium means you essentially abandon NVIDIA, because doing 2 at the same time is hard, right? And so that is a tough choice. That is a tough ask for people. Rightly so, in my opinion.
And you can run which kind of model
all of them.
This?
All of them.
When you say all of them is...
LLMs, image,
but it
voice.
Works with Llama, it will work with OpenAI, open source.
Yeah, all of them.
All the models that you have open weight right now on...
Even closed weights, we worked with Poolside to make their models run. Yeah, on,
so it can
Trainium.
It can work on
it doesn't really matter whether it's...
So basically what you're doing...
As long as we have the weights in the code and the architecture, not the codes, we will make it work.
So you have the plumbery of the... you are working on...
It's an ML framework, it's open source, github.com/ZML/ZML. It's the technical foundation by which, number 1, we write models. Number 2, we abstract the hardware. So it is also about abstracting the hardware in the sense that, because there's many things about abstracting the hardware. It's how do you talk to the hardware? It's how do you leverage the hardware software to, run at maximum capacity? Because our premise is that NVIDIA knows how to program for NVIDIA chips.
And it's become CUDA.
So, or cuDNN, or like all the libraries that make the CUDA ecosystem. But the thing is, they have operating complexity that you have to. So we bring all of this, by the way, this is all open source, and we bring all of this into this framework called ZML. github.com/ZML/ZML.
That means also that a chip provider can provide into ZML on open source his own way to access his hardware.
Right, but the interface doesn't have to be open source.
Okay.
And that's very important because what you want is, or at least what we want, is to allow hardware providers to differentiate without opening too much of how their chip work. Because it's important that we have competition on the market.
And you're not forcing the model of the competition. Everyone can decide wherever he chooses to. And why did you not host this kind of product on top of a big foundation or something like that to gain stability and audience?
Because there's a product line to be made and the opportunity is bigger for us to be a for-profit company.
Yeah, but you can be a for-profit company working with a foundation.
Oh, I don't know. Laziness.
Laziness, okay.
we built it. There was no, let's just say, trying to capture money on a framework is weird, to say the least. And so, but also
there is a good company working on framework and being rich. Like GBoss, Oracle.
Yes, but the framework is free. Our framework is free.
Yeah.
So this is the thing. And also, by the way, there was a question about should we make our, I would say, chip agnosticity open source? And to me, the answer was yes, because we all have, as a founder, I have a vested interest in competition, existing.
Openness, yeah.
Yes. But also, most importantly, the customers, the users have, an interest in this thing to happen,
That's something very important in the digital world is like customers and users have interest inside breaking the monopoly, which is something that we don't do right now, but I think it would be interesting.
But there's many reasons, by the way, but it's always a good thing that there's competition. It breeds, innovation. It breeds efficiency, and so for this, we figure it was best to have that part open source because we want more. We want more actors in the field.
Okay, so that's those developments. So maybe what you can do right now, because we continue the discussion, but at some point we all need to go to bed after 5 weeks meeting all together.
It was long 5 weeks. We ran out of batteries. The eagle eyes will have seen maybe the difference.
Yeah. So, what is your view on the market right now, and what do you announce for the market for the next few months or year? What do you think would happen to the market of AI? How do you run it? And in a glimpse of understanding why it's important to invest right now on AI and this kind of situation.
Look, it's going to penetrate the entire economy, plain and simple. How many times in your life will you have something as transformative and has, I would say, wide, ripe for the taking? There's not that many opportunities. Mobile, if you were not developing for mobile, not a lot. There's many, sides of the economy that don't really, need to have a mobile presence, right? even though, mobile, there's more phones than people. Imagine something with an open ceiling that will penetrate everything, in which everybody is racing against, and the odds are not, settled. So it's, all of us for the taking. And so I think, we should invest in it, or at least spend a bit of brain cycle into it. I know I am. On the altar of, there's not that many opportunities that can be as transformative as AI is. Everybody is trying to figure out, we're all, searching for like products, usage, technologies, but it's very much a gold rush. And the opportunities are incredible. Whether it's, by the way, financial, society, politics, it's very, very intertwined. And it's very, very much the beginning. It may crash. Maybe we're in a bubble, but it will not die.
When we say bubble, for example, the dot-com bubble, we said the bubble.com have crashed. Yeah, a lot of people have lost a little bit of money.
Yeah,
but did the bubble really crash? Do you stop using internet?
Did it kill internet? No.
Yeah. Does internet stop changing the society and the way we live? I don't think so. So yeah, maybe there will be some overhyping and on too much starification and survalorization of some company, but at the end of the day, the way AI works will change the world forever. And yes,
it has, by the way, changed the world.
Yeah.
Maybe in our little, you would say, privileged bubble, for sure. But it has at least the potential to change it for literally everyone.
Yeah.
And that, by the way, in that sense, is the book is like it's still unwritten. So there's a lot of, it's up to us to write it. And don't, believe, the bullshit. We are very, very much at the beginning.
So as I often say, it's computer, it's about the software. ZML is a software company. I'm very confident about what they're doing. Right now, I hope that the few episodes have make some people understand a little bit more about the economics and the point of making AI and how does it compute. So that was Opening Voices. Thank you, Steve.
Thank you, Quentin.
To come there. Go to zml.ai to understand more about ZML. And we will see in a few weeks for a new interview inside Opening Voices. Thank you very much.
And keep building.
Thank you for listening to Opening Voices. The conversation between Quentin Adam and Steeve Morin will continue in a few days, so follow us and subscribe not to miss our next episode.